This one says find the best order to integrate and do it, and the next one, it's basically the same thing where there's two options. One way is going to be easier than the other. So I'll just do one of these two since they're so similar, and it doesn't matter to me which one we do. In some ways, this one will be more, I guess it doesn't really matter. Does anyone care which one we do, 6 or 8? You want to do, that's this one?
Second one, yeah.
Okay, we'll do
Yes,
this one.
that one. That
All right,
one.
we'll do that one. We'll do that one. We can do it. Okay, so we can either integrate with respect to x or integrate with respect to y first. It doesn't really matter. Both are possible here. So let's suppose we want to integrate directly without switching the order of integration. Let's suppose we want to go with the x. So what I would do is think of this as follows. So remember that when we do a partial integral with respect to x, we're thinking about y as constant.
Are we missing a power to the 1/2?
Yes, we are. Minus 1/2. And so when we see that, that's not dissimilar from a typical integral that you've done lots, where you have something like the integral of x plus some constant. If you wanted to integrate that, or if it was to the minus 1/2. You all know how to do that already, right? You'd add 1 to the exponent, divide by the new exponent, and then do a reverse chain rule if necessary, if the coefficient of x was not 1. So we can do that here. We can, the 3y piece is just constant. The 3y is just a constant that sits in front. So we don't have to get all freaked out by it. So that 3y is just going to come along. And then we add 1 to the exponent. So we're going to get x plus the, let's see, which there. So we're going to get x plus 1/2, x plus y half, oh geez, x plus y squared to the positive 1/2 divided by positive 1/2, which means multiplied by 2. The reverse chain rule, the derivative with respect to x is just 1, so we don't have to worry about that. And then this should be evaluated from 1 to 4, and I should be erasing this integral right here, because we just integrated with respect to x. Does that look okay to everybody? With respect to x, we're treating the y as a constant. We're going to then just use the regular old power rule, and any y is coming along for the ride. So now we're plugging this in for x. So we'll have 0 to 3. We can pull a 6 all the way out to the front. And plug it in for x, we have 4 plus y squared to the 1/2. So y times 4 plus y squared to the 1/2. Then we're going to subtract off the value at 1. So minus y times x plus 1 to the, whoops, plugged it in for the wrong letter. Get it in for x. So 1 plus y squared to the 1/2. And we have that. Does that look okay to everybody? And there's a square on that y.
Said it.
Right there. It's there, it's there. Okay, so we want to integrate those, and those are both, each of those quantities is integrable by sub, u sub. So if we let u equal this, and then over here we're going to let u equal that, and then both of those will come out really easily. U sub. We looked at that one similar
But we
today.
can't use the same. You can't use.
But we
like-
can't just let the same u, yes. We have to do them separately.
We tried to do.
We tried to do a shortcut, but no, you got to do 2 separate integrals there. Does that make sense to everybody? Yeah?
We would do with respect to y first, so we need to use.
Yep, so if we wanted to do it with respect to y first, we would if we wanted to go with respect to y, so with respect to y, we're going to let u equal x plus y squared. And then du will be 2y dy. And so that will work perfectly fine also. And sometimes folks ask, when we're doing these partial integrations, why do we use the regular derivative differential, and that's just sort of tradition. That's how we do it. You are doing a partial integral by holding y constant, but we just use the regular dx. We don't put a partial dx in there. Just use the regular dx, even though it is a partial integral. Okay, does that help on that one? All right, so let's jump over to the 13.2 stuff. The first one here, sketch the region of the integration and evaluate the following integral. I'm not sure exactly what the question was here.
Oh, finding intersection points.
Finding the intersection points? Okay, so is it clear what the graph is if we go from y equals 0? So y equals 0, what's that? X-axis. And then 2x plus 4, just a line with a slope of 2. So we're kind of in these, we're sitting in we have a few of them here that might work. And then y equals x cubed. So x-axis, 2x plus 4, y equals x cubed. So it looks like we're at this one, letter B. Okay, so horizontal or vertical element?
Yeah.
Oh, definitely matters.
Definitely matters.
Horizontal.
Because
horizontal.
this part down here, I mean, you could do it with a vertical element, but then you're going to have to break it into this region, which has the cubic as the lower curve, and that region that has the x-axis as the lower curve.
Yeah, let's not do that.
So you could do it that way if you subdivide it. So it makes probably more sense to go with the horizontal element there. So let's do that. We'll go with the horizontal element. So if we go with the horizontal element, then dy dx or dx dy?
Dx dy.
dx dy?
It's always normal to the last thing.
Say that again?
It's always like the direction of the integral, or like the element
Yep.
is always perpendicular to the last, like if it's dy. it's
Yep,
perpendicular.
exactly. That's right. That's right. It's always perpendicular to the axis of the second differential. Right, it's perpendicular to the y-axis. So then our function, what was that? 6x squared. That's going to go in here. And then our limits of integration. Okay. The inner integral is representing the functions. So we have to have x values. So we have to go from x equals whatever to x equals whatever. So this first line, let's get that written as an x value. So come up here, solve for x. So we have 2x equals y minus 4, divide by 2. So we're going to have x equals minus 1/2 y plus, or minus 2 actually. I guess that's a plus there.
There you go.
There we go. Subtract 4 and divide by 2. Subtract 4 and divide by 2. Correct. And then this one written as an x value will be x equals the cubed root of y. And then put in our limits. So the left curve is going to go on the bottom here. So we're going to get 1/2 y minus 2. The upper curve is going to be the cubed root of y. And then the y values are going to go from 0 up to 8.
How do you know it's 8?
I looked at the picture.
But how could you
All right,
work
so
out
if we, so I'm just assuming that it's 8. So obviously we would have to mathematically show that. And that looks like did they put a T on this problem? They did not. Let's take a look, because that does look
If you multiply
complex.
both by
Couldn't figure
2,
it out.
if you
Let's-
add
I was like, I don't know.
Well, let's figure it out.
both by 2 is 8.
Right.
What if I- what if
All
I-
right, so we
Because
have
if we
that.
said-
Well, you know what you would normally have to do, right? What do you do to both sides of that?
Oh, you cube it.
You'd have to cube it. I mean, when I'm looking at that picture, I would obviously give you curves that intersect at a reasonable point. I'm not going to have you cube something. So when I look at this picture, I see that 8 is the candidate. And I plug 8 in here, and I get 4 minus 2, which is 2. I plug in 8 there, and I get 2. I see that 8 does work. So in a case like this, it's probably easier with trial and error and looking at the graph.
Some of them won't give, they're not nice, some of them.
Some of them.
Yeah,
not
they're in the
nice.
middle of like the,
You tell me when you find one that's not nice, because I won't give you one that's not pretty reasonable. But I want to make sure that it's really not nice and that there's not some sneaky way that you could get at it. So what we would have to do this manually is cube all this out, which we're not going to do right now. Cube it out and solve that for y, which would be hard. It's going to be a little bit of work. Did you cube it all out, and was it factorable?
No, but I can see like it'd be 2 times 2 times 2 at least, so there's
Right.
something there. I don't know.
Yeah. So that'd be the mathematical way to do it, though. And then if that doesn't come down to something that's factorable, then you'd have to use technology. So on the test, I'll definitely have you set curves equal to each other that will end up being pretty easily solved. I will not ask you to do that to a binomial. That just is too time consuming. And
The way I did it is I broke it down into multiple integrals, like by region. Is that?
Yep, totally fine also. Yeah, so and maybe that will have less, if you did a horizontal or vertical element.
I did.
A vertical and separated it here and.
Yeah, I split it in the center, so I just
Yep.
like negative
Yeah,
0 to
that
0,
definitely
and then from
works.
0 to 2. It made it a lot easier.
Yeah, if you separate it like that and
It
then
came out
this other
something nice,
side.
like 96, I think.
Right.
So.
Yeah, so that's another option is to go that way and break it into 2 regions. Yeah.
It is. It's a nice number. I like nice.
All right, let's take a look at this one, which is 14. This one's a hard one. Let's go to 15 for a second because that's an easy one. And I won't go all the way through 15, but I do want to go all the way through 14. Let's just talk about this one for a second because it's pretty straightforward and it gets at an idea that we're going to use with the previous one. So when we look at this, we have a plane. There's a plane z equals 6 minus x minus y. That's a plane. And one type of graph that you want to get comfortable doing is the tetrahedron graph. You'll have a lot of these planes that they give to you where you can actually sketch the part in quadrant 1 really, or octet 1 really easily. And that's going to sort of look like a tetrahedron. And when we look at this, if we want to know where this plane intersects the z-axis, we're going to let x and y be 0. So z would be 6. And then if we want to know where this tilted plane intersects the x-axis, we will let y and z be 0. If we let y and z be 0, we get that x is equal to 6. And if we want to know where it intersects the y-axis, we let x and z be 0, we get y equals 6. So you can actually sketch this one you can get a pretty good sense of what's going on here. So you have that tilted plane. And if you imagine the 3 coordinate planes, you have a tetrahedron. And so this says compute the volume with that base. So we've graphed part of it in the first octant. But obviously it goes through the xy plane, it continues back, it goes on and on forever. Okay, so the important thing here, when we look at our region of integration, let's draw that separately. When we think about our region of integration, that's down in the xy plane. And we're talking about a unit square, at least many of us will call that a unit square, or maybe many of us wouldn't. So that square where the radius is 1 for a square, which we probably hate to say. Okay, so we have a square that goes from -2 to 2, -1 to 1, so it's 2 across and it's 2 up. So that square we're imagining down over here in the xy plane, and let's just try to get that in there. And it goes behind the z-axis there. And there's the y-axis coming through. So all we need to know is that that plane is sitting on top of that square. That's all we need to know. If we want to find the volume of the column beneath that plane on that square, all we need to know is that that plane's up here. Because we have to know what surface is on top and what surface is down below. If we want to find the volume between these, we do upper minus lower. If that plane happened to go through the xy plane so that it was below the xy plane and we wanted volume, we would have to do upper, which would be z equals 0, minus the lower, if we wanted volume. You could also do whatever you want to do, and then if you get a negative, just make it positive, because then you say, oh, well, then it must have gone through the xy plane. You'd That's a possibility.
So you're saying that if it goes through the XY plane, you have to do something different to account for the volume
Yep,
that's
so
below?
just like
Okay.
we did with area, if somebody says to you, find the area of this, you would have to get area, you would have, and let's just say this is y equals f of x, you would have to integrate negative f of x from a to b to get area. Because if you just integrated f of x, you would get negative 1 times that area. So if you did just integrate straight across here, we'd call this signed area. So it would take whatever's above and subtract off whatever's below, so you get that signed area. Same thing with volume. If your surface undulates through the xy plane, but you just integrate straight across your region, you're going to get upper volume minus lower volume. So in this case, the only thing that we have to acknowledge is that, oh, this plane sits above that square no matter what. Now, if that square was an 8, if it came all the way out to 8 in all directions, that would be totally different. Then it's going to be going below the xy plane. But for this particular plane and that particular square, this sits above. So all we have to do is integrate that plane. That's our upper surface. And it does not matter whether we do dy dx or dx dy. We go minus 1 to 1, minus 1 to 1. Does that make sense? So the plane is sitting above, and if we want volume between two surfaces, we do upper minus lower. The lower surface is z equals 0 in this case. And that's a pretty straightforward integral. So that's going to just sort of help us a little bit with the previous one, which is much harder. So this one says, compute the volume of the solid bounded by the planes below. So we have a bunch of planes there, and they're going to trap some solid object, and we want the volume of that. And we're going to need to know whether we orient ourselves with a lower and upper surface, whether we orient ourselves with a back and a front surface, or whether we orient ourselves with a left and a right surface. Because to find the volume between two surfaces, you have to do upper minus lower. But if it was in this direction, we would have to do front minus back. And if it was in this direction, we'd have to do the right minus left. So just like we did area, right minus left or upper minus lower, with volume, you have 3 orientations that are possible. And we have to ask ourselves the same question. Which direction do we want the element to go? Which direction has a defined upper and lower surface throughout the whole column, or whatever they're going to call it? Which direction gives us the unique right and unique left, or unique upper and unique lower all the way through, or is it mixed? Well, let's find out. So for this one, we notice that with x and z, we just have constants. So that's pretty straightforward with those 2 dimensions. So x equals 0 out to x equals 5. So I'm just thinking that in my head. I've got a back plane of x equals 0, a front plane of x equals 5. And then we think lower and upper, z equals 0 and z equals 6. So now we've got caps on the lower and top. The lower surface and upper surface are planes. So really, it's these 2 things that are going to cause the lateral bounds for this solid object. So let's graph those. Let's go over to, it's always very, very helpful to graph your domain in a totally separate place so that you can get a really good sense of what's going on. So the domain for over here, when we graph those 2, we're going to look in the yz plane. So the first one, z equals y minus 3. So it's a slope of 1, y-intercept of, or z-intercept in this case, of -3. So we have something like that, where this is down at -3 and this is at +3 there. The other one, slope of -2, also has a y-intercept of -3. So it looks like the slope is -2, so it's going to be coming down like that. So we want to just get a general sketch so that we can kind of get it going. So let's see, what is the y-intercept here? Y-intercept is going to be -3/2.
Oh.
The y-intercept right here,
Oh.
is that -3/2? Negative 1.5. Do you agree?
Yeah.
Negative 1.5. So negative, let's put a 1, put a 2, and then a 1, 2, 3. So that's sort of what's going on. So the important thing now let's try to assess what we really need out of this sketch. Because we've already said we only care about what's above the xy plane, z equals 0, and what's below z equals 6. So when we come over here and look, we really don't care about all this stuff down here. The important stuff is where z is equal to 0, that's right here. And then when z equals 6. So z equals 6 is going to be a line across here. We intersect that at 6. 5, 4, 3, 2, 1, 0. So the part that we really care about is all of this right there. Okay, so that is the region in the YZ plane that we're talking about. And now with these equations, x is missing. So we're going to then pull this in the x direction if we're trying to graph it in a three-dimensional coordinate system. Right? The x is missing. So now we extrude in the x direction. So let's just try to translate this over to here, get at least a reasonable idea of what it looks like. Let's use red. So we've got something like this. That comes down to 3. That comes down somewhere in there. And then we're going to come out this direction. So it's going to be some, and it's not coming out as far as I'm making it look actually right now. Let me make it a little bit less, because it's only coming out to x equals 5. So I don't want to get too crazy with it here. So you get the general sense of what it looks like. And that's tilted down there. Yeah, it's kind of hard to draw. But something sort of like that. Maybe I should make the lines that are behind it dashed. Yeah. Yeah, it's close enough. So we took that shape in the YZ plane and we pulled it along the x-axis, getting a trough. And so we've got a drywall mud trough, just a trough. And what this tells us is the direction of the direction of integration. What surfaces should we pick? Is there a unique upper and lower surface? If we drop a vertical line parallel to the z-axis, do we have a unique upper and lower surface? Come over here. So what I just said, if we drop vertical like that, okay, here's the upper surface, there's the lower surface. But then I come here, and now I have an upper surface which is uniform, but a different lower surface. Here the lower surface is that diagonal plane. Here the lower surface is the xy plane. So bad direction for the surfaces. How about if we go front to back? Do we have a unique front and a unique back? Yes, we do have a unique front and a unique back. This is the back surface, and when we pull it forward, we'll have a unique front surface, which would be x equals 5. So that's a possibility, for sure. What about unique sideways surfaces, left and right? Yeah, those are also totally uniform. If we draw this element across that direction, it hits this plane first, it hits this plane second, and no matter where you draw a horizontal element, it will meet the same left, it will start at the same left surface and end at the same right surface. So we now have two choices. We can integrate with either the x's on the inside or the y's on the inside. Which let me show you a quick analog. So if we had the double integral of something, I'm just making stuff up here. Let's just suppose I had something like this. I don't even care what the x limits are. Isn't that the same thing as the integral from 0 to 5 of x minus 1 dx? Right? So the idea if we were finding the area, a double integral to find area, we could either use a double integral or a single integral where we're going to do upper curve minus lower curve. So that's the upper curve, that's the lower curve. So it's the same idea with surfaces. So what surfaces do we want to use? Do we want to use front and back or left and right? Front and back?
Sure.
So if we use front and back, then we're going to go like this to figure out the area, or the volume. So we're going to do a double integral. The front surface was x equals 5. The back surface is x equals 0. So we're going to do 5 minus 0. And now the two letters that are left are dy and or y and z. Which one comes from the constant interval? Z, so we're going to have to go dy dz. So we did front surface minus back surface. And now the domain is right up here. And let's kind of clean this up a little bit. Let's get rid of some of this superfluous stuff. And so that's our domain. That's the domain we're going to use. We have to use a horizontal element. If we don't use a horizontal element, then we are not going to have a unique situation. We'd have to subdivide it. So there's our element. And the z's we said are constant, 0 to whatever that z-intercept was, which was 6. And then the y's are going to go from that left curve to the right curve. So the left curve is this one right here. We have to solve it for y. So that's going to give us 2y equals, if I add that over there, subtract the z, divide by 2, we get minus 1/2 z minus 3/2. So that's the surface on the left. That's this one. The surface on the right is z equals y minus 3, which if we write it as a y value, that's y equals z plus 3. So that's the right surface. So we're going to put in here the left to right, so minus 1/2 z minus 3/2, and then z plus 3. So that would be using a dy dz. We also could have done the other option. That's very easy to integrate. The 5 comes out as a constant. We integrate dy to get y, so we do this minus this. So that won't be too crazy. So, or if we did it the other way, so instead of using front and back, let's use left and right surfaces. If we do left and right surfaces, then the right surface is this one. The left surface is this one, so we would go like this right away. That's the right surface minus the left surface. And now z is in there, so we would have to use as the domain x's and y's. So let's come back up here. X's and y's are down here in the xy plane. The x's and y's, that xy domain, let's graph it separately so that we can get a good sense of what it looks like. So down here, let's put it over. Actually, I've got some lines here that we can use. Let's reuse these. We'll recycle you. Okay, so down in the xy plane, how do we figure out what the domain is there in the xy plane? Isn't it just a rectangle?
Yeah.
Rectangle. So the y interval goes from where to where?
Negative 1/2 to 3.
Negative 1.5 to 3. So negative 1.5 to 3. So negative 1.5 to 3. So we're there and there. And then that's y, that's x. And how about the x's?
0 to 5?
Yeah, 0 to 5. So this is our rectangle down in the xy plane. So in the xy plane, we've got that as our domain. And does it matter with that rectangle whether we do dx dy or dy dx? Yeah, it doesn't matter because everything's constants. Now, there is one catch, though, for sure, which we will get to in a moment. So x's are going 0 to 5. we'll do dx, dy. dy goes from -3/2 up to 3. Okay, so now this surface, though, we've got z as the variable there, which is bad, because we're integrating with respect to x and y. Let me just think for 1 second there. What did we just do?
We pulled the z's as opposed to pulling the y equations.
So those were y's. Oh, I'm sorry. So this should, oh, crap. So if we did y's, what should the domain be? If we did our surfaces with y's,
dy dx.
so if the surfaces are y's, then what are the two missing variables? Yeah, x and z. I don't know why I picked x and y. Sorry about that. It should be x and z. It's got to be x and z. I don't know how I went that direction. And of course, if there's a z in there, we've got to integrate with respect to z first. We can't have z on the outside, so let's redo these limits then. So x, y, that's not going to matter so much. We need the xz plane. So the xz plane is going to be the plane that is formed over here. So if we sort of imagine the xz plane here, it's still a rectangle. It's still a rectangle. X is going 0 to 5, and z is going
0 to 6.
0 to 6. So z would go 0 to 6, and x would go 0 to 5. Yeah, we don't
Are
need that
your
one.
Oh, wait,
Z's
those are
on the
reversed.
inside?
Z's are on the inside. Oh, I'm sorry. So we will put the 6 there and the 5 there. 6 there, 5 there. Thanks. Okay, so there's two different ways we can think about it. So we treated the perception is different. Here we have a front surface and a back surface. And then here we have y equals this and y equals that. So this is a right surface and a left surface. So this is right and this is left. This is the x equals 5 is a front surface and x equals 0 is a back surface. Just keep that on the burner. We're going to do lots more of this. We need some more imagery though to make it all make sense. Okay, now once we have those set up, the integration is very simple. They're both, this is linear and that's just a constant. So the integration is simple. So let's keep going then, and we will get some pictures where we do more of this front, back, left, right, up, down stuff. So let's get to, we didn't finish 2 though, right? We still have like 3 or 4 slides on 2. So let's finish that first. Let's see, where are we at? I think we're right there. Because this is going to be where we start to see, the first few problems, they give us some nice pictures to try to orient us here.
Did we do the one before this? I feel like number 66 on the couple problems on the previous slide, and I don't think we did the second one.
Oh yeah, you're right. Right at the bottom. Thank you. Okay. Can you integrate that with respect to y? No. There's a y to the 5th in the denominator. If it was an even power, you could use trig sub somehow, but y to the 5th? No. So we have to go with respect to x. So our goal then is to rewrite this. We're going to have the same integrand, but we want to go with respect to x first. All right, if we want to go with respect to x, these aren't constant limits, so we can't just swap them. So we've got to draw the picture for what that domain looks like. So let's write it out first. So I would write, this is how I would write it. I would say y equals square root of x to y equals 2. So those are functions of x. We're going from the square root of x up to y equals 2. Those are functions of x. And then we're saying x equals 0 to x equals 4. So let's draw that domain, and then let's reverse the integration. So we know what square root of x looks like. And we're going to y equals 2. Okay. So we're going from square root of x up to y equals 2. So we've got y equals 2 right there. Let's draw it with a line. So then we analyze the x's. And the x's are going to go 0 to 4. So that's right. It lines up perfectly with that intersection point. That point right there is 4, 2. And the region that we're playing around with is this region in here. Okay? So they had a vertical element to describe that region. And we know it's on that side because we're going from square root of x up to 2. So we know that's the region. Now we want to swap the integral. So we're going to switch the order of integration by using a horizontal element instead of a vertical element. This tells us that the y values are now constant. They come from the interval 0 to 2. The x limits come from the boundaries of this element. They go from x equals 0, that's the left boundary. Now we have to write the right boundary as an x value. We'll write it as x equals
Y squared.
y squared. That will be our upper limit. Now it's easy to integrate. Now it's simple to integrate. The y to the 5th plus 1, that's just a denominator. It's just a constant. So we get x squared over 2. So x squared over 2. Put the over 2 bit out front. And that's going to be evaluated 0 to y squared. And when we do that evaluation, then we have a perfect situation for logarithm. Because now we get y to the 4th, or y to the 5th plus 1. It's almost in log form. To force it to be in log form, what do we multiply the top by? 5. And then we have to multiply the denominator by 5 on the outside. Now it's in log form. So now we can jump right to our answer. That's going to be 1/10 natural log of the absolute value of the denominator, evaluated between 0 and 2. Plugging in 0 gives nothing. So all we have to do is plug in the 2. So this is an example where we have to switch the order of integration for the integral to even be manageable for us.
Are you gonna say that on the test?
Switch the order of
it?
integration? Yes.
Okay.
Yes. Yeah, I don't want you writing this as y to the 2, to the 3, whatever.
Well, I'm just saying, like,
Try it, yeah,
you're not
no.
gonna make us be, like, recognize
Guess.
it.
No.
Okay.
No guessing.
No guessing.
I'm sure you might guess some other things, but.
Not
All right,
that.
any questions on that? Okay, well, let's get to this one. So here's where we start to see these pictures and where I can probably describe to you more easily what the allowable directions of integration are. So when you look at this, that wedge object, do you see that you have a unique upper and unique lower surface? So if you drop a vertical line parallel to the z-axis, do you see that you could use that there's going to be a unique upper surface, which is this tilted plane, and a unique lower surface, which is z equals 1? So there's no ambiguity there. There's no subdividing of the solid object. There's a cap. There's a ceiling and a floor. Distinct. There's no weird skewing. Right? What about if we went left to right? So y equals 0 out to this area over here. Would we have a well-defined right surface and a well-defined left surface?
Yes.
Yes.
Okay, so certainly the left surface is y equals 0. That's the left surface. Now, if you imagine yourself in this rectangle over here, so you start there in that rectangle, and you start moving to the right, eventually you slam into the surface, right? The tilted plane, right there. What about if you're way over here in the corner? When you start moving out towards the lateral edge, the right edge, Are you going to hit the plane, or are you going to hit the turning part of this cylinder?
You're gonna hit the edge of the domain.
You're going to hit the edge of this cylinder here. So you're not going to have a unique right surface, because this whole boundary is turning right there. So if you come left to right, you are not going to hit the plane first if you're down low enough. So you don't have a well-defined right surface. So you do not want to treat it as right minus left. We can treat it as upper minus lower. Can we treat it as front minus back?
Yes.
So if we go front minus back, do we have a unique front and a unique back? Yes. In the back, there is a triangle. And as you move from the back towards the front, you're never going to move outside of this plane. There's no way you're going to hit this tilted plane first, because that plane is perpendicular to the YZ plane. So the YZ plane back here is perpendicular to that, because there's no x in this equation, so it's being pulled out along the x-axis. So if you're back there at x equals 0, when you come forward, you're going to hit this twisting front piece. So you have a unique back and a unique front. You have a unique bottom and a unique top. But you don't have a unique right-hand side. So we have two options when we want to integrate this. Now, just like when we're integrating to find the area of something, the more intuitive direction is left to right, vertical element. That's the direction that's going to be the most intuitive, the least likely to cause problems. With surfaces, most of the time, upper minus lower, if it works, if you're allowed to do it, is going to be the simplest, because you can picture the upper surface, you can picture the lower surface. Like lots of you, I could see, were having trouble imagining the right surface here. That's a lot harder to do. So if you can use upper and lower, that's the way to do it. If you can use upper and lower, do it. So if we want to set this up as upper and lower, we're going to do the double integral of the upper surface minus the lower surface. So here we have upper surface, here we have lower surface. Upper minus lower. And that means our domain is down in the xy plane, which they've already drawn for us, so that makes the most sense to use that also. If we wanted to use the front-back thing, we're going to have to draw the domain over in the YZ plane. So upper minus lower, we've got the domain down in the xy plane. The domain is just the projection of the intersecting curve between two surfaces down here. So in other words, if we have two planes and we let Z be eliminated, that's going to generate the curve down in the xy plane. If we set these two equal to each other, 1 equals that, then we get that y is equal to 1. What did I just do? Oh, I set the wrong things equal to each other. The two surfaces that we want to set equal to each other to get this curve down here are this cylinder and this intersecting plane. I don't want to set these two planes equal to each other. Those aren't the ones that we care about. We care about this curved cylinder and that tilted plane. So we would set those equal to each other. And that cylinder is right here. Y equals 1 minus x squared. So y equals 1 minus x squared. There is no z in it, so we take y equals 1 minus x squared and we pull it vertically in the direction of z. We extrude it. That's what's creating this parabolic cylindrical wall. So that thing down there, they've given it to us. Y equals 1 minus x squared. So let's go ahead and draw that separately. It's always very, very smart to draw your domain separately, because it's very easy to get tangled up in madness when you're trying to interpret a two-dimensional domain from a three-dimensional graph. So here's our domain. We just care about octant 1, which corresponds to quadrant 1. So there's our domain. Right there. Our domain is just sitting in quadrant 1. So y equals 1 minus x squared is that curve. And so should we use a vertical or horizontal element?
How about vertical?
Vertical makes
Well,
the
it
most.
doesn't matter.
It doesn't matter, but if we chose a horizontal, we would then have to solve this for x.
Yeah, let's not do that.
So we've been given a function of x. So if you're given a function x, it makes the most sense to just use a vertical element because you've already solved for y. You already have it written as a y value. So that makes the most sense. So then when we come back to our domain over here, our integrand over here, we've got this integrand, and we've now decided, so this is in the y direction, that's in the x direction. We've now decided that we want dx on the outside. So we're doing dy dx. X is coming from the constant interval 0 to 1. Y is coming from the variable interval 0 to 1 minus x squared. So that will be our integral. That's the upper surface. That's the lower surface. Okay, so now in this case, that makes the most sense. If you can do upper and lower, go for it. That makes the most sense. But if we wanted to do, we could do front and back. So we set it up with front and back just for grins. Let's do it. Let's set it up front to back. So if we want to set it up front to back, the volume is going to be, we're going to do front surface minus back surface. Front surface minus back surface. So our domain is now going to be in the YZ plane, because our front surface is x equals something, back surface is x equals something, so the domain is going to be in the YZ plane. So we've got the YZ plane, and then x is telling us how far to come forward or how far to go back. So now we have to set up our domain in the YZ plane. So we come over here, again, always draw your domain separately. It gives you the best chance of understanding everything that's going on. So we look at this. We know we've got this tilted line right there, z equals 2 minus y, which again we said is a line with a slope of -1 and a slope of -1 and a z-intercept of 2. But then we stop at z equals 1. So we're going to go down, and that is going to be our domain in the YZ plane. So that's our domain in the YZ plane. That line right there is z equals minus y plus 2. Slope of -1, intercept of 2. And then they tell us to stop at z equals 1. So z equals 1 is this lower curve, if you will. All right? And now we have two choices. We can use a horizontal element or a vertical element. Does not matter. Very easy because that diagonal line is a line, so we can easily solve for y if we have to. Let's do it. Let's use a horizontal element. Will, you have a question?
All right, I was just thinking that probably we could do a vertical element since
Yeah.
that's already solved for z. But
Yeah, exactly. Normally we would just choose a vertical element because it's already solved for z, but let's not do that this time just because it's easy to go the other way. Let's see if we can manage it. But yeah, you're 100% right. That would make more sense if you were just trying to do this as quickly and as efficiently as possible. But we're trying to be creative here, so we're going to choose an element that direction. So that means our constants are going to be from the z's. So we're going to have a dy dz. And z is going to go 1 to 2. That's on the outside. And then the y's are going to go from the left curve, which is y equals 0, to the right curve, which is y equals minus z plus 2. And now in here, we did front minus back. So now we have to get our front minus back. So our front surface is what? How do we define our front surface? It has to be x equals something. And our back surface is certainly x equals 0, the way they've given it to us. So the front surface minus the back surface.
That would probably have something to do with our original region.
So this right here, right, isn't the front surface this parabolic cylinder right there? What is that? That parabolic cylinder. So if we want to write this as a front surface, again, this wouldn't be the most intuitive way to do it because we have to solve this for x. So we would have that. And then we would take the square root. And would we choose the positive or negative square root? Are we dealing with the half of the parabolic cylinder that's where the x's are positive or where the x's are negative? Where the x's are positive, we would choose this.
I think you dropped the negative side. You had negative y plus 1.
Oh, right on the inside. Thank you. Thank you. And so that would be our surface that goes in here. Square root negative y plus 1. So that's front minus back. Front is this. Back is just the x equals 0 plane, which is the yz plane. So those will give us the same exact volume. Doesn't matter.
One's obviously easier.
Yeah, top one's easier. This one's a simple enough one that we can kind of try it a different way.
Where did you get your outside limits on the second one?
So these two.
Yeah.
So if we come over to our, bless you. So the limits for our double integral always comes from our domain. So both these sets of limits come from this domain. We chose a horizontal element, so the z limits are constant. That element's perpendicular to the z-axis.
Okay.
So z
Got
equals
it.
1 to z equals 2. And then horizontal element means we have to define this curve and this curve as y values. So we get a y, right y minus left y. All right, let's look at another one. These things just take a ton of practice because they are weird. It's very difficult to sort of see sideways when you're dealing with these. All right, so here we have a parabolic cylinder right there. There is no y in there. So if you were to graph this in the xz plane, you would get that parabola, but there's no y, so you then pull it parallel to the y-axis. So you're going to have this parabolic trough coming along the y-axis. But then they chop it off with these planes. So that parabolic trough is coming along, but then we have a diagonal plane that cuts it off here. We have a vertical plane that cuts off and makes a backside to it, like a parabolic wedge now.
Like a scoop.
Pardon?
Like a scoop.
Scoop. It's like a scoop. Exactly. It's like an ice scoop.
I was thinking more like the Sprouts ones for bulk, but yeah, that works.
So, or that. Or if you're trying to scoop your granola. We need a handle on it. I'm not going to try to draw it. Okay, so is there a unique upper and lower surface? Yes. So we have this parabolic trough coming along, and then we have this diagonal plane that chops off. And so the parabolic cylinder is always below, and that diagonal plane is always above. So we definitely have a unique upper and unique lower surface. So that makes the most sense. That's the way we would want to go. Do we have a unique left and right surface?
Wait,
Yes.
Which is left and right?
Left and right are always with respect to y.
Yeah, then yes.
So the left surface is that. So we have our trough coming along, and we have that diagonal plane that cuts it off. This could act as the left surface, the diagonal plane, and the right surface would be this vertical plane at y equals 1. You see that? Okay, how about back to front?
No.
Yes. Yes, because we've got this parabolic trough. So the back side of the parabolic trough is always the back surface, and the front side of the parabolic trough is always the front side. Yeah.
I think I may have missed when you said, like, how do you determine if they're unique or not?
Yep.
Like, is it just what you just said, if they are, I don't even know.
So your question is this. So when we do it in 2 dimensions, it's way more intuitive. It's way more easy to see. Like if we draw this region here in 2-dimensional space, you would tell me, oh, there's a unique left and a unique right. Because no matter where I draw that horizontal element, there's the same left and the same right. And you would say that there is not a unique upper and lower because here you have this as the lower curve, but here you have that as the lower curve. So you don't have a unique up-down situation.
So it has to be in all places.
All places. So you're imagining all possible horizontal, or in this case, y elements, x elements, z elements.
Although technically with this one, front and back, technically the same curve.
Yeah.
And that works.
Yep,
okay.
that works. So like if you were integrating on a circle, right? If you were integrating left to right here, you would go from negative square root over to positive square root. right? So if you have a parabola, same idea. If you were going to integrate left to right, if this is y equals x squared, and you go horizontal, then this is x equals negative square root of y, and this is x equals positive square root of y. So it's that idea. So it can be the same surface, but different parts of it.
So this one is unique because there's no curve or anything, so that's why you can go from the negative to the positive, because that top plane isn't curved at all.
Exactly.
Okay.
Because that top plane is cutting right through that parabolic trough. Now, if it was tilted in this direction also, then all bets would be off. But that plane, the way it tilts, it's not coming down on itself. So if we go front to back, we never hit the plane first.
Okay.
So that plane is coming down like this, so that parabolic trough always has the back of the trough to the front of the trough uniquely defined. Now again, they're not asking us to do that here, but you want to take every opportunity to try to see left, right, back, front, and up, down. Because the better you can visualize it, the more likely you are to write the correct limits down.
So if we had, like, if that z equals y plus 1, if that had anything to do with x in the equation, then it wouldn't be?
Exactly. Since there's no x there, that means it's being pulled parallel to the x-axis, so there's no way it's tilting, and there's no way you could draw an element from back to front that would then hit it. Because there's no x, if you draw an element parallel to the x-axis, it can't, you're right? It can't run into itself. But if that plane that's above the trough, if that plane were tilted, then you could draw a horizontal element that would hit the plane before it hits the trough, possibly.
Isn't it tilted?
It's tilted in the other direction, though. Like right now, this is tilted, but it's right. It's being pulled parallel to the x-axis. So with respect to x, it's not tilted. So when we're thinking about a back-to-front situation, we're drawing an element parallel to the x-axis, and because that plane is also parallel to the x-axis, we're never going to run into it. We're going to start at the back side of the trough and hit the front side of the trough because that plane's not tilted and in the way. Okay, so let's do it up-down because that's what they asked. Okay, so the volume double integral, upper surface minus the lower surface. And then we have to have a dx and a dy. So we go look down in the domain, and we have to decide, should we do a dx dy or dy dx? Well, like I said, graph the domain. It really helps. It really helps to have the domain graph separately. And the graph of the domain, this is an example that didn't follow through with the last example, but will follow through here. We have z equals y plus 1. We have z equals x squared plus 1. The domain is the intersection curve projected onto the xy plane. So that right there, if you take a light and shine it down on it from far above, you get that parabola down in the xy plane. So if you set these two equal to each other, you will get the curve in the xy plane. If you take two surfaces and eliminate z, you end up with the intersecting curve of those surfaces in the xy plane. So
Well,
if
because
we,
won't you get just the ones will cancel out, and then you'll just get y equals x squared?
yeah, exactly. So we have x squared plus 1 equals y plus 1. So we get y equals x squared. That's this curve right there.
And yeah, you wrote a y equals 1.
Oh, thank you.
I do that. I make that mistake quite a bit in
Yeah.
physics.
So easy. I mess up the easy stuff.
Or I don't know that they have the same button on the keyboard too.
That I would not have been able to say off the top of my head. Okay. Now we know that this is stopping at y equals 1. So this parabola of intersection goes on and on and on, but they tell us to stop at y equals 1. So y equals, oh boy. So, yikes. So y equals 1 is this upper curve right here. Y equals x squared is that one. So again, it makes most sense just to choose a vertical element. So we do a dy dx. That makes the most sense. This one, it's kind of a hassle to go the other direction because then you're taking the square root of y. We don't like taking square roots if we don't have to. So we'll just go with what makes the most sense and not try to make it more complicated than we have to. So we're going to go y on the inside. So y has, that element is bounded by y equals x squared and y equals 1. And then the x's go from -1 to 1. Integrate that with respect to x, with respect to y, and then with respect to x. And we won't go all the way through the nitty-gritty. The 1's cancel here, so we have y minus x squared dy dx.
And we could cut it in half for symmetry. Yeah.
And this is an example where we can clearly see that there's symmetry, so instead of -1 to 1, we could go 0 to 1 and double it. Absolutely. All right, let's take a break. Let's take a break, and then we'll do some more SurfI.
I have a question for you. So in the book and the examples here, this one shows that we have a parabolic equal above and like a paraboloid above and a paraboloid below. Would we just, is that another one where you just do like upper minus lower then?
Yep.
Just for that?
Yep. So if you have a paraboloid opening up and a paraboloid opening down, you're going to do upper minus lower. And then that intersection curve, you'll set this one equal to this one, which will eliminate z, and that will give you the curve down in the xy
I was
plane.
thinking you could just like, I don't know why I was confused. Like an element.
Yeah, so yeah, when you look at those two, when you look at your vertical elements, oh, and so here they're actually, and I just misspoke because I had some problems. The intersection curve's not going to matter here because they told us that we're just on this triangle.
She posed that way. It's given behind the dome.
Right, here it's given, and that's what this pink wall is there, because those paraboloids would intersect, but they're chopping off part of it. So that's why there's that sheer wall there, because they didn't allow us to figure out where the intersection is. They want us to just restrict it to that triangle with this intersection.
Okay.
I know.
Yep.
Yes. I know. Do you need peanut M&Ms? What?
No, just A.
That makes a lot more sense. Where's the x?
So it comes when,
I don't think
so we're going to have, when we multiply both sides, so we're going to set this equal to x over that.
Right, yeah.
And then when we multiply,
You just kind of forced the calculation.
Pretty much.
the multiplication should take care of it. So multiplied by that, we're going to get a times x plus 2. And then we get b times x plus 1 equals x. So watch when we, so do you want to use method, the
Oh, yeah.
convenient value method? So if we plug in -2, we get 0. We get negative b equals -2, so b equals 2. Plug in -1, we get 1a. Plug in -1 there, so a equals -1. So if we have -1 over x plus 1 plus 2 over x plus 2, when you get a common denominator, the x appears.
Oh, okay.
So when you get a common denominator, so you're going to get -x plus 2x is x, -2 plus 2, so you get back to this. Yeah, so whenever this is linear, then this is just constant. Whenever,
I just don't understand why the x.
yeah. So that's how the x appears. When you get your common denominator, the x will appear.
Thank you.
Yeah, you're welcome.
I had an idea about what you'd suggested.
Yes.
About maybe doing things after class, but since I can't stay very long, do you think maybe after class we could do like 1 or maybe 2 problems each
Mhm.
day, just so that I mean that's at least over time.
Yeah, that builds up.
Problems.
Definitely. That's a great idea.
Because I think what's happening during class is that I feel like I'm following along during class, but I
Mhm.
think that it's going so fast that it's not really
You're
sinking
not retaining
in.
it. Yes,
Um,
definitely.
and then when I try to remember later, it's a mess.
Distant. It's a distant memory. Yep, no, that's a great idea. We'll do 2 right after.
And like you can pick whatever problem you think might be best.
representative.
Or get what we talked about.
Yep. I like it.
You should.
I like it. It makes perfect sense. Oh, the wind.
It's not like, it's like $200, so it's not like that a lot.
Mm-hmm.
It couldn't be like.
Entirely sure how to go with this problem.
So let's see. So and that screw goes all the way down?
Yeah.
Or no.
The whole thing?
No.
So if we integrate with respect to y,
She got so.
you want to probably break it apart like this.
My advisor for the scholarship.
So if you're going to integrate that with respect to y,
On the walls, on the floor.
are you supposed to switch the order or
No, this is just
because whatever? Okay, so with respect to y, then this just sits out there. And that all comes along, and then this goes up to y to the plus 1/2 divided by 1/2 means multiplied by 2. And then whatever the y limits are. So that's really 16. So then you plug those into that. So plugging in 16 is going to give us 4, so then it'll come to the front and give us 8. 0 doesn't give us anything. And so then we can do the same thing now with the x to the half. Make it x to the 3/2 times 2/3. So the key is that when they're multiplied together like that, we're just going to treat this one as a constant. That root x is just a constant. So it's just like integrating 5y to the negative 1/2.
It's pretty tough, like, if I could double integral of like x squared plus, or x squared plus y squared, x squared.
X squared plus y squared.
I mean, they're both in a parentheses squared. Like,
Twitter.
Like Kendall one.
They would look like that.
Yeah.
There was nothing else in it.
I don't remember. I don't know what this is.
So then we just have to square it all out.
Okay.
So we'd have to square it all out. Go that.
And I've seen kids
Kind
throw
of-
those off.
I think it's.
No, I don't. I'll look at it after class.
Yeah, I guess
I think there was more to it. That's why it was.
So if it's this, we'd have to square it out. There's no
Right.
shortcut with the u sub. And then we're going to integrate with respect to x. Get x to the 5/5 plus 2x cubed over 3 plus x times y to 4.
I'm allergic to
And that's usually, supposedly it's supposed to be really
It
simple.
might have been.
Yeah, take a look.
Yeah.
If there is, we can look at it.
And you can barely run on.
Yeah, that's what they do.
Yeah.
Hard to
So that's the
run.
first time I've laughed in hours.
The dog. Fire really
dog?
does not like it.
What happened?
So you need that
Yeah.
It's like I looked at him this morning, he was like sitting.
I mean, I'm not laughing, that was like,
How old is he?
all the fair,
No,
you would
he's like
walk
jumped
back
on
to
and off
something
beds
else.
and stuff his whole life, and all of a sudden he's just like, I was like, I'm the worst dog.
Well, yeah, it is a cute clone, although it's good
So easy to.
Dogs are crazy.
It's
I'm
hard.
never gonna be able to have children because if this way this makes me feel like a dog. It makes no sense.
No, that means that you'll take good care of your kids because you've learned.
Right to learn. I've had tons of animals. My daughter
Tough.
has no broken bones.
Yeah. And sometimes when they get cancer, they'll have like weird sort of things happen like that.
I don't think so.
The last dog got cancer at 8,
Really?
and one day was running all over the place, going on 6 mile hikes. Literally 48 hours later, she was dead.
Yeah.
It's crazy.
Wait, donuts?
A dog.
Donuts.
Oh.
Yeah, no, dogs and cancer.
Dogs. Cancer. We
Oh,
took
that's
her, and
rough.
she woke up and all wasn't moving. We took her to the hospital. They said, "Oh, let's give her some medication, take some X-rays," and then 24 hours later, she's dead. Like crazy.
Is that fracture? You go high back. Yeah. Oh, sorry.
And sad, very sad.
That's very reasonable.
All right, let's get rolling with. Oh, did I even pause the thing? Oops.
Sarah.
At least no one was saying anything totally weird.
Yeah, now they
The
just get to
mic
hear
picked
about
up.
dogs. Sad dog stories.
Sad dog stories.
Yeah.
Sad dog stories.
Red Dog 2.
Ooh, so sad. All right, so we've got a couple more to go. Let's get those done. So, and I've put this on the board before, and it kind of matches with what we've seen with a single integral. And we know that with a single integral, you are just getting the length of the interval, b minus a. So a single integral of a differential is just the length of the interval. Whereas a single integral of a function is giving you area. So we have length, then we have area, and we have the same analog here. If we do the double integral of an area differential, we get area. But if we do the double integral of a function, we get volume. So in other words, we can use a double integral to find area instead of just a single integral. And it's really 6 of one, half dozen of the other. It doesn't matter which way you do it. So here it says use double integrals to compute the area of the following regions. So let's set up a picture. X equals 0 is the y-axis. X equals 4 is the line over there at 4. Y equals x. We have that diagonal line bisecting quadrant 1. And then as our last bound, we have, what's that, 2x plus 1. So that's a little bit, we need a little more space. Let's stretch this out. So 2x plus 1 has a y-intercept of 1 and a slope of 2. So I'll just do it sort of like that. And x equals 0, that's the y-axis, so let's put that there. So that's the region that's trapped between those 4 curves. We have 4 curves, 4 boundary curves, and they generate this region here. So if we wanted to find the area of this region, we know how to do it with a single integral. Single integral, upper minus lower, that would give it to us. Or we can use a double integral. It doesn't matter. So area, if we write it as a double integral, clearly we're going to pick a vertical element, correct? I mean,
Clearly.
unless you're super ambitious, which, yeah,
Is that volume by slicing? Like back in the day?
this right here,
Yeah.
this
Area by
is,
slicing?
this, yeah, kind of, if you think of each cross section as the area, so that's kind of what we're doing. If we think about the cross section of a solid object, this would find the cross-sectional area. So back then what we did was integrate area to get volume with a single integral. And so we could use a double integral of something where it's just all in the limits and it's not in the integrand. Or, yeah. We could make that argument for sure. It's a little bit different though. Because here we're just finding a plane. Here we're finding a plane, an area of a small region of the plane. And so what is the outer integral? Should it be x's or y's?
X's.
So we're going to put x's on the outside. So we're going to do dy dx. And the x limits are 0 to 4. The y limits are from y equals x to y equals 2x plus 1. So that's the area. And if you just do the first integral, the inner integral, let's make sure this is super clear because it is going to happen a million times the next month. If we're integrating a differential, just like I wrote above, you just get upper limit minus lower limit when you integrate a differential. There's no y here, so we're integrating just the differential. So we end up with the upper limit minus the lower limit. That's it. Upper minus lower, 2x plus 1
Plus
minus
minus
x. minus x.
So x plus 1?
Yeah, exactly. So x plus 1 when we simplify it. Right? So if you were asked to do this in Calc 1, find that area, right? That's what you would have done. You would have just set that up. You would have said, oh, it's the single integral of the upper limit, the upper curve minus the lower curve. Or maybe not in Calc 1, beginning of this class. I don't think they did this in Calc 1 yet, or anymore. So you can so the single and the double, you can see the connection. The double turns into a single of upper minus lower. That's what it does. All right.
I get 12 for that, right?
I get 12 too. I got
12, yes, we get 12. 12 is the answer. So the wedge sliced from a cylinder that passed, the wedge sliced from the cylinder by these two planes. So that x squared plus y squared equals 1. If we were in 2-dimensional space, that's just a circle. But we're in 3-dimensional space. And there's no z. So that means we have a cylinder. We pull that curve in the xy plane, that unit circle. We extrude it in the z direction. So that builds a right circular cylinder. But then we have two planes that chop it in half, or that's a bad word. Chop through it. They don't chop it in half. Trying to chop an infinite cylinder in half gets a little suspect.
But isn't it, can't you just cut it anywhere and you properly cut it in half?
But we
It's an equally infinite amount on the side.
yeah, maybe. We'll have to ask Vsauce. All right, so we've got our cylinder, we've got our two planes. Now, this doesn't take a lot of visualization because one of the planes is the upper plane, one of the planes is the lower plane. Right? So we really just have to figure out which one's on top. So let's go and look at the domain. So these planes have no y in them. So that means they're extruded in the y direction, I guess that way. So we're going to graph them in the xz plane. So let's graph those in the xz plane. So xz plane will be our domain in this case to graph these planes. So let's just get a sense of, this is just to get a sense of which one's on top. So we know that they're going to be in the xz plane and pulled in the y direction. So 1 minus x is just a diagonal line like this. And the other one looks like the the z-intercept is -1 and the slope is going to be 1. It looks like they're going to intersect right there. Okay. And that point is, this is at 1. All right, so now we can kind of visualize what's going on. So the cylinder is just a vertical right circular cylinder. This is going to act as the upper plane, and this is going to act as the lower plane. And the cylinder has a radius of 1. So that's perfect. They intersect right at the edge, and it's going to create some sort of weird, wedge type thing. Like, that's supposed to be 3-dimensional. Oh boy. Yeah. So, it's going to create some sort of wedge-like thing like that.
It's perfect.
That's not bad. That's better than I would do.
Just imagine taking a hot dog and chopping it like that.
I was going to say macaroni.
Or macaroni.
Oh, is it?
Like disformed macaroni.
So you've got the cylinder, and there's one plane that cuts it diagonally this way, creating some sort of a diagonal ellipse. And then another one that cuts it that way, creating another diagonal ellipse. And then you've got that weird wedge.
So why do you have two wedges?
Because there's an upper plane and a lower plane that's chopping that cylinder. So the cylinder is a right circular cylinder, and there's one diagonal plane that's making a ceiling, and one diagonal plane that's making a floor. So this is acting like the upper surface, and this is acting like the lower surface. And to draw this probably a little bit better, this piece, if you're trying to graph it, should probably be dashed because we can't really see it. That's back there, behind. Okay, so we need to know which one's the upper one. The upper one was the one that had a bigger z-intercept, So this, the upper one is z equals 1 minus x. The lower one is z equals x minus 1. And that's all we need to know. Now we know the upper surface. Now we know the lower surface. So the volume is going to be the double integral of the upper surface minus the lower surface. So 1 minus x minus the quantity, x minus 1. And now we have to figure out, should we do dy dx, dx dy? Let's draw the domain. The domain for our solid object is down in the xy plane, right? We said it was a unit circle. So there's our domain. That's in the xy plane. Vertical or horizontal? All right, we'll do vertical. Now, that means that we are going to go with x's being constant. We're going to go dy dx. X is going to go minus 1 to 1. You can make an argument for symmetry here, if you're careful. Sometimes it's better not to use symmetry if you're not 100% certain that you're subdividing the solid object perfectly in the middle. How about the y limits? What's the lower y limit?
Negative root. That's 1 minus x squared.
1 minus, so that's 1 minus x squared. So that's the lower semicircle. And then the upper semicircle, 1 minus x squared, square rooted with positive. So that's our setup.
But aren't your x's going to cancel?
What's going to cancel?
X. Oh, no, they're not.
The ones will cancel.
The ones will cancel.
The ones will cancel. So we'll have negative 1 to 1.
2x, sorry, that's what I meant.
The ones don't cancel.
The ones won't cancel.
We'll get
1.
2 plus 2.
Oh, those don't cancel either.
No,
Nothing cancels.
nothing
Minus
Well, that's
2x.
sad.
Minus 2x
I
plus
was really
2.
hoping something canceled.
Yeah, nothing cancels. Okay, so we get that. Now, is there a y in that integrand? No, no y. So what do we do with this inner pair of limits?
Multiply it.
Multiply by upper minus lower. So this is going to be negative 1 to 1. We have negative 2x plus 2. That's just a constant with respect to y. And then we have the upper square root minus the lower square root, but it's minus a minus, so it becomes plus. So we end up with this integral. That's going to be 2 times the square root, 1 minus x squared dx. And then we would factor. We'll go all the way through this one because it's got.
Did you forget a parenthesis on the square root?
That one?
Yeah.
Thank you. So let's pull out the constant of 4 all the way out to the front. And then negative 1 to 1. So then we have negative x plus 1.
Where'd you get the 4?
Yeah, where'd you get the 4?
2 times 2.
Wow! I did an Owen Wilson meme here and say, wow!
So we're going to pull the 2 out there and then also that 2. Pulling up both those 2's.
Did you say Owen Wilson?
Yeah.
Wow!
Owen Wilson.
Bad I don't know who Owen Wilson is.
He's a funny guy.
Terrible.
You should look him up.
You have to look it up immediately.
You need to watch Wedding Crashers.
Yes.
Or Shanghai Noon.
Oh, that's Shanghai Noon is good.
Yeah, Shanghai Noon and Wedding Crashers.
So good.
If you have time, Night at the Museum.
I've seen Night at the Museum.
He's the cowboy.
Ah.
Okay. So we have to bust it into 2 integrals.
Can't think about calculus anymore. All I can think about is Owen Wilson.
Don't start laughing.
Just saying, wow!
So does everybody follow the 2 integrals? We distribute the square root to each piece. Distribute the square root to the negative x. Distribute it to the 1. Okay, so how do we do the first one?
There's going to be some tricks up.
Yeah.
The first one we do with u sub. First one's simple.
Second one's tricks.
First one is simple. Second one we use
Trig.
You could use trig sub, but there's a much easier way.
Magic. Radial.
Yes!
Magic.
What did he say?
It's a magic circle.
A circle?
It's a magic circle. So this right here, what is that graph? Y equals the square root of 1 minus x squared. Isn't that the top half of a circle of radius 1? And if we integrate that from -1 to 1, isn't this just the area of a semicircle? So this is just the semicircle area. So the area of a full circle of radius 1 is pi, so the area of half of a circle of a semicircle is pi over 2. So y equals the square root of 1 minus x squared. That's the upper semicircle of a unit circle. Integrating across it, -1 to 1, that means finding the area of a semicircle, so we can use pi r squared, and then divide that by 2.
And then multiply by 4.
And then at the end, multiply by 4. Here, we're going to let u equal 1 minus x squared. So du will be minus 2x dx. Divide by 2. And we have minus x dx all taken care of. So that first one becomes, we have 4 outside. This is going to become the integral of, what, just square root of u divided by 2. So u to the 1/2 divided by 2, we'll put that there. If we change our limits to u limits, ooh, yeah, let's do that. What do we get? What do we get? 0 and? 0. Yeah, that's great, because that's 0.
Yeah, let's do that.
Goes away. Excellent. And then we have plus our pi halves. Pi over 2. So our final answer? 2 pi. Or not 2 pi. Perfect. That is the question.
I have a quick question. Is there some way that we would have been able to notice that was going to go to 0 to begin with?
Well, that's always a good question when you look up here. I don't know what the graph of x times square root 1 minus x squared looks like, but what it tells us is if we graphed it, it would be symmetric on this interval.
Yeah.
So there would be just as much area above as below, which is why it goes
If
to
we
0.
did symmetry over here, do you think that would have, if we used a symmetry?
So now the question on symmetry, we have to be really careful because the way that this thing is chopped is in the x direction, right? It's chopped, and these two faces are moving in the x direction. So we just have to make sure the way we set it up so the way we set it up is not proper for symmetry. We would have to use a horizontal element, and then we could use symmetry. Because a horizontal element would be going in the x direction, so then the top half would have the same amount of area or volume as this half. But it's not going to be true that there's the same amount of volume here as here, because of the way that there's that diagonal cap on it, right? So if you have a diagonal cap like this, front and back have the same amount of area volume, but not left and right, right?
Would GeoGebra be able to give us a visual on that if we put everything in? Okay.
Yep, yep, definitely. Yeah, it'll graph it pretty nicely, actually. Okay, let's carry on. Oh, thank goodness. All right, so 13.3. Polar. Polar. We're going polar.
You look amused.
Okay.
So amazed. Yeah.
All right, so you all know how to convert Cartesian curves into polar curves. Use x equals r cosine theta, y equals r sine theta, right? You can go back and forth. X squared plus y squared is r squared. Tangent of theta is y over x. We're not going to do that here. But what we are going to do is look at a polar region in the xy plane as our domain. And what we need to do then is figure out how to change a regular double integral with a function of x and y. How do we change it to r's and thetas? And the trick is going to be to convert the differential. So we've been integrating f dA, and we've been turning our dA into dx dy or dy dx depending on which way we wanted to integrate. But we want to figure out how to write our dA in polar. And the key is that it's going to be equal to r dr d theta. That's how we're going to write an area differential in polar. And so they have a little argument here about how to figure out the area of this polar sector. So this polar sector here is what our dA is going to be. And so we're trying to correspond a rectangular area element with a polar area element. And what they did up here was find the area of the large sector, subtracted the area of the small sector, and then they took a limit. And that's how they come up with r dr d theta. So if you're curious about doing that in detail, we can do it after class. But the main point is that we're going to take a rectangular area element, dx dy, and we're going to merge it into a polar area element. And the area of a polar area element is r dr d theta, period. That you have to remember, r dr d theta. That you have to remember.
Got you, 2 grand.
r dr d theta.
Already.
All right, not rdr, r dr d theta.
Why do I want to say oi, oi, oi?
I don't know. You tell us.
We're all gonna remember this.
Because of that movie with Owen Wilson.
Oh my goodness.
Okay.
It's
So
the Owen Wilson movie where he calculates double integrals over polar rectangular.
So that's it. So the dA, instead of becoming dx or dy, or one of the other dx dy or dy dx, it becomes r dr d theta. And almost 99% of the time, you'll go dr d theta, not d theta dr, because it's going to be much easier to have it. Most of our polar regions will have theta coming from constant intervals. So there'll be rays emanating from the origin. So it'll be theta equals pi over 6 to theta equals 2 pi over 3 or something. So it's going to be easier to have your thetas constant most of the time. And when we write our polar curves, we write r equals something. So r dr d theta. Let's do one. R dr d theta. R dr d theta. Don't forget.
We're all gonna remember that.
I know, it's impossible to forget.
RDRD
RDRD theta. RDR. So anytime your domain is a circle or a disk, boom, polar is probably going to be the way to go. So here we go. So find the volume of the solid below the paraboloid and above the following regions. So there's 2 of them. So we've got this upside down paraboloid, 4 minus x squared minus y squared. So it's, x squared plus y squared looks like this, minus x squared minus y squared looks like this, and then they shifted up 4. So, and then we want the volume beneath that and above that disk. So here's what we're going to do. It's going to be remarkably easy. So that, normally when we want to find the volume between 2 surfaces like that, we do upper minus lower, which we still do. The lower surface is equals 0. The upper surface written in polar is 4 minus r squared. That's the upper surface. X squared plus y squared is r squared. So we just replace x squared plus y squared with r squared. So that's the upper surface. And then instead of dx dy or dy dx, we put music to my ears. Yes. So that is how we rewrite the dA differential. And watch how simple this is. So when we come up with our limits for r and theta, what are the limits for r? The radius is going from 0 to 1. We're starting in here and we're going out radially 1 unit. So we start at the origin, we're going out radially 1 unit. So we're going from 0 to 1. And how far are we going around the circle? 0 to 2 pi. That's a heck of a lot easier than having the last one that we just did, minus the square root of 1 plus x squared, that thing. 1 minus x squared. A lot easier. Way easier. And then we can just plug and chug. Now here's an efficiency step. Do you see a theta inside this integrand?
No.
No. Will there be a theta after you do the inner integral? No. So this outer integral can immediately be collapsed into the length of the interval. So right away we can say 2 pi. So we can put a 2 pi on the outside right away. So that's because the outer is with respect to theta. There's no theta in the integrand, nor will there be a theta in the integrand after we evaluate the inner integral. So we can get rid of the outer one right away. And then with the inner one, we just integrate. So we can kind of do that in our head. We have 4r and r cubed. So we integrate 4r, we get 2r squared. And then minus r to the 4th over 4. And that's 0 to 2 pi.
No, you mean 0 to 1.
0 to 1. Sheesh. Thank you. 0 to 1.
Should that be inside the parentheses technically?
Which?
The what, I don't know what you call it, that vertical line.
This evaluation
Yeah.
bar? This says to the evaluation bar says to evaluate whatever is in the parentheses from 0 to 1.
Oh, okay.
So that's totally fine how it is. And plugging in 0 doesn't give anything. Plugging in 1 gives 2 minus a 4th. So that's, what is that? 8/4 minus 1/4. 7/4. So we have 2 pi times 7/4. And that's going to give us 7 pi divided by 2. That'll be our volume beneath that upside down paraboloid and above the unit disk. Now, let's have a slightly different region. Let's have a partial annulus. So the region of integration, we have a partial annulus. So an annulus is going to, we're going to go from r equals 1 to r equals 2, and theta pi minus pi halves to pi halves. So the partial annulus is right in here. So that's going to be our region of integration. That's our domain. That's our capital R. And then volume is equal to double integral. 0 to 2 pi was the outer integral. The inner one
would
is
it be still be 2 pi since we're...
Why did I say that? Thank you. Minus pi over 2 to pi over 2. And our inner one is going to go 1 to 2. And we had 4 minus r squared multiplied by r d theta. R d theta. And that's it. So we integrate. So for imagining our polar element, the polar element is coming out of the origin, and it hits the inner curve, and then it hits the outer curve. So it's from r equals 1 out to r equals 2. And then that polar element is sweeping from minus pi over 2 to pi over 2. And then we integrate and plug in our values, same old same. So is there a theta in there? Nah. So we can just pull the length of this interval out as a multiplier. So that's pi. That's the length of the theta interval. We integrate, we get 2r squared minus r to the 4th over 4 from 1 to 2. Plugging in the 2 gives 8 minus 4 minus, plug in the 2, bless you, minus 2 and plus a quarter. So we get 2 1/4, which is 9/4, so 9 pi over 4. Yeah. 9 pi over 4. Is that right? 4, yeah, I think that's right. All right, so that's the volume that sits above that semi-annulus and below the paraboloid that's upside down.
gets to name the shapes?
Some doctor.
Whoever makes it up, or?
These things were named so many thousands of years ago. I have no idea who made the word annulus up.
The Romans?
Greeks, Romans.
The Greeks, the Romans.
I don't know.
Human beings somewhere.
Some human somewhere. You're so Earth-centric. Okay, another one. We have a hyperboloid this time. We want to find the volume of the solid below that part of the hyperboloid and above that disk. So again, not too complicated, especially with these first ones. The upper surface is the hyperboloid. We want to write it as a polar hyperboloid. So we just replace x squared plus y squared with r squared. The lower surface is the xy plane. That's z equals 0. And then we replace dA with? Oh.
RD theta.
Excellent. Well done. Well done. You'll never forget. So r goes 0 to 2. Theta goes 0 to 2 pi.
And we can just do collapsing thing again, right?
Yep. There's no theta, nor will there be a theta. So we'll collapse that outer integral to 2 pi. And then on the inside, 0 to 2, let's go through this a little bit. Distribute the r.
Why wouldn't we do U substitution?
We can. Aren't we still going to have to do a distribution though? We'd still have to distribute and get 5u.
Well, 5 U is
Or
not-
5, or 5 whatever.
That's not too bad.
No. But here won't be too bad. We'll just get that 5r squared over 2. Yeah, either way that would work. You could sub right away. 1 plus r squared. That would work for sure. For sure. Okay, so this is 2 pi. And then the first part here is 5 halves r squared. And that's evaluated 0 to 2. The second part, we're going to use u sub. So u will equal 1 plus r squared du, well, less u will be 2 r dr. So du over 2 is what we're looking for. So we'll end up with minus 1/2 integral. So let's plug in our u limits. So we get, what's that, 1 to 5? Does that look right? Plug in 0 for r, and then plug in 2 for r, and then we're going to have square root of u. So we will have 2 pi times 10 minus 1/2 u to the 3 halves times 2/3, 1 to 5, close parentheses. There. So, what do we get? 1/3, 10 minus 1/3. And then plugging in the 5 is going to give us 5 root 5. Plugging in the 1 gives us 1. So we're going to have 1/3 times 5 root 5 minus 1. Got all that. Etc. You can combine a couple of constants in there. If you distribute the 1/3, you can combine the 1/3 with the 10 and distribute the 2 pi. Question?
Can you remind me? I think I remember us talking about the 3 halves sometime back.
Mhm.
I've come across a billion of them in the homework.
Yeah.
And I'm wondering, is there a way to sort of pull it apart? You just called 5 root 5.
Mm-hmm.
Is that's because of the 3 halves, right?
Yes, exactly. So if we have 5 raised to the 3 halves, you're right. In the homework, we see it a ton. So that's square root of 5 cubed. So when we have 3 square roots together, 2 of them combine into 1 inside.
Okay.
Yeah, you see that a ton.
Makes you want to like, it makes you want to make it into 25 because it's like, well, you square a square root and then you get the number. That you square that number, you get the square of the number, and it's like
Tempting.
all right,
Yeah.
Tempting.
Because it would be so nice if it was like that.
Yeah, if it was 4 halves. All right, so then we want to do the same thing on this interval. We don't need to go through this, the same idea. We have the same exact integrand, we just have different limits. So we have constant R limits instead of the R limits that we had above. We have those, and we have that for our theta limits. So it's going to be the same integrand, same antiderivative, different evaluation. Nothing complicated. All right, here, let's try another one. So sketch R and evaluate the integral. Okay, so the region here, can you visualize it? It looks almost identical. It's that semi-annulus thing. Ooh, semi-annulus. And we're going from 0 to pi. So we're going to have the top half. The upper semi-annulus. Get that stuff. Ooh. Oh, I can't erase. Okay, any questions on the setup? Pretty simple. So then our volume. So we don't, now we're getting to the point, we have this surface here, we don't even know what it looks like. It's 1 over 1 plus x squared plus y squared. But we know that it's positive. So we know it sits on top of that annulus. We know that there's no signed volume that we have to deal with. Right? The thing is above the xy plane for sure. So our volume is going to be the integral 1 plus r squared r dr d theta. And 1 to 2 for r, and 0 to pi for theta. No pi, nor will there be a pi. So we can collapse the outer integral, make it a pi. Then we have 1 to 2. And isn't this set up beautifully for log? Put a 2 there, put a 2 down there. So then we get pi over 2 multiplied by the natural log of 1 plus r squared, 1 to 2, pi over 2 ln 5 minus ln 2. And we probably want to stop there. So that'll be the volume beneath that surface. Samantha?
Most of the examples have just like x squared plus y squared or negative of that. Could you maybe do like 20 because it has 2x squared plus y squared and negative x squared minus 2y squared.
Yeah, so that actually will probably, it's going to be very...
Is it just a little more complicated? You get to
It's a tiny more complicated. What we'll do is replace the x with r cosine theta and the y with r sine theta. So we'll just introduce a sine or a cosine. So that's going to be like this one. Let's do this one. This one will kind of, it's a little different, but it will have the theta in there also. All the ones we've had so far, like you said, have no theta. So let's do one with a theta. This one will have a theta in it. So it's going to be like what you're saying. So if you have 2x squared plus y squared, you're going to have an r squared, but you're also going to have an r cosine theta. So if you have thetas in it, here's what they'll look like. So let's try to figure out this one. We have a circle of radius 2 centered at the origin. Okay, that's our first curve, circle of radius 2 centered at the origin. And the second curve. All right, that's one of those circles that's tangential to the x-axis or the y-axis. We probably have forgotten which. So let's just plug some points in. Theta equals 0, where are we at? Theta equals 0, what's the r value? 0, so we're right there. Go up to theta equals pi over 2.
We're at 4.
We're up at 4, so we're about right there. So it's going to be a circle of radius 2 centered at 0, 2. So that will be the circle. So that's a radius 2 circle also. And so that's one of those things that, as long as they're very simple to graph, as long as you remember that a constant times sine or a constant times cosine, it's a circle that's tangential to an x-axis or y-axis. So the sine ones are all tangential to the x-axis, the cosine ones are always tangential to the y-axis. Okay, so we want to find, what does it say? So we want to rewrite this as an iterated integral over R. So we want the region that's outside the first circle and inside the second one. So that is this region here. Okay, so there's our region of integration. That's our domain of region R. And we need to imagine our polar element. So our polar element comes from the origin and goes out radially. So one thing that we've noticed also with our polar elements is that we've been very lucky, and we wouldn't use polar if this didn't work. There's a unique inner curve and a unique outer curve. So we've had all disks so far, so the inner curve is r equals 0, just the origin. And then the outer curve is the perimeter of the circle. So here, do you agree that if you rotate your polar element around, you have a unique inner curve and a unique outer curve? So this makes perfect sense for polar then. You want to have that condition that you have a unique inner and outer curve. Now the thing we don't know is theta. We have to figure out, okay, we know that R is going to go from the inner circle to the outer circle, but we need to know what these 2 points of intersection are, there and there, because those are our theta limits. Theta is going to go from whatever that right quadrant 1 angle is over to that quadrant 2 angle. So we set them equal to each other. So we set 2 equal to 4 sine of theta to find our intersection point. This tells us that sine of theta is 1/2. This tells us that in our picture, theta is equal to pi over 6 or 5 pi over 6. So this angle here is at pi over 6. And the other one's at 5 pi over 6. Now we can set up the integral. Now we can't use symmetry or anything because we don't even know what the function is. They're saying just set it up. They're just wanting us to set this up. So we have f, and then we are going to use the RD theta, so it's going to be f times RD theta. The R limits we said were 2 and 4 sine of theta. The theta limits are pi over 6 and 5 pi over 6. Now in this case, could you collapse that outer integral into upper minus lower? No. Because the inner integral has theta in it. So there will be thetas that appear in the integrand after we do the inside integration. So here we don't have that luxury.
Oh, it just said express.
Yeah, that's it. So that's all they wanted us to do. So that is all they wanted us to do.
Can we put an F in there too?
What about the F?
Do we have one? Do we have one? Like can
Yeah.
we do top minus bottom or right minus left or?
Right. So if we have a surface that we could write as polar,
Oh, never mind.
right? Makes sense. So if we had the paraboloid,
It's gonna give us something when we. Okay.
yeah. So if they gave us a surface like the paraboloid, we plug the paraboloid in and subtract off the lower surface, which may be the xy plane, which would be just 0. Okay, so region inside both the cardioid and the circle of radius 1 centered at the origin. Okay, so let's get graphing. So the cardioids that we're expected to be able to manage are these simple ones. And these are the ones where the coefficient of the cosine or the sine and the constant have the same magnitude. So those we should be very comfortable with. So if it's something like a plus or minus a sine of theta, or a plus or minus a cosine theta. Those are all cardioids that are very simple to draw. So those are the ones that we'll be dealing with. And again, who knows which way the dimple is on that cardioid. So we'll let theta be 0. Cosine of 0, 1. So cosine of theta is 1. 1 minus 1 is 0. Doesn't help a ton. Start rotating. Pi over 2. Cosine of pi over 2.
0.
Subtract that from 1.
1.
And we get 1. Come over to pi. Cosine of pi.
-1.
-1. 1 minus minus 1. Then we're out at 2 from the origin. So we're over here. That's enough. We now know that this point's going to be here. We now know that this is the cardioid that we're dealing with. That is the cardioid that we are dealing with. And then we have our circle of radius 1 centered at the origin. That's going to be right here. I should draw that one first. Okay, so I think we want the area
It has to
of
be
the
inside both.
kidney being in there. That thing right there. All right, so that's the area that we're trying to find. So that. Okay. Let's first observe that we can cut this into pieces, 2 pieces. This piece over here is just a semicircle. That piece is the semicircle, the left half of the unit circle. So we know that. So the area of that green region right there, the region I'm pointing to, that's 1/2 pi times the radius squared. So the area of that half will be pi halves. Then let's find the area of one of these chunks here. So the area of that is going to be, whatever it is, we'll eventually double it because we've got 2 of those little lobes. So area of that, we're going to use a polar element. So it's going to be double integral of r d theta. R is coming from the origin and moving out to the cardioid. It's doing that. So it's going from 0 out to 1 minus cosine theta. So 0 to 1 minus cosine of theta. How about theta for that little lobe?
0 pi over 2.
0 to pi over 2. 0 to pi over 2. So there's our integral. And then when we're all done, we'll double that and then add the pi over 2 from the semicircle. So let's integrate this. There is going to be a theta that appears, so don't get trigger happy. Leave that outer integral there. Then we get r squared over 2, evaluated 0 to 1 minus cosine theta. That will be found by squaring the upper limit. So we're going to get 1 minus 2 cosine of theta plus cosine squared of theta. And that 1/2, let's go ahead and just put that on the front of the integral. And then what identity do we need to manage that cosine squared? We're going to have
Sine squared.
yeah, we'll have to power reduce it, right?
Oh, 1/2 plus 1/2.
Yeah, 1/2 plus 1/2. So we're going to do 1/2 plus 1/2 cosine 2 theta. And that 1/2 can combine with that 1. So we're going to get 3/2 minus 2 cosine theta. And then 1/2 cosine of 2 theta. Now we're ready to integrate.
Can you write the identity you used?
1/2 plus 1/2 cosine 2 theta.
It's a double angle identity, right?
1/2 plus 1/2 cosine 2 theta. And then sine is the minus
And then we integrate. We end up with 3/2 times theta minus 2 sine of theta, integral of cosine of sine. And then plus 1/2 sine of 2 theta divided by 2. Yeah, that's a dot. That's a multiplicative dot. And then 0 to pi halves. It looks like we have a bunch of cancellation. This goes away for either one, correct? Sine of 2 pi over 2 is the sine of pi, which is 0. Plug in 0, sine of 0 is 0. So that goes away for both. And then the other two terms alternate which part they go away for. So we'll get 1/2 times 3 pi over 4 minus 2. Oh, I guess that one, that doesn't go away at all, I guess. Minus, I guess this goes away totally for 0.
Yeah.
That goes away for both, but this goes away for 0. So that's what we get.
And we have to multiply that by 2.
Yeah, we still have just found the area of, and we have to add the other pi over 2 thing. So what is that? 3 pi minus 8 over 4. So 3 pi minus 8 over 8. All right, so we're almost there. The total area is 2 times that plus pi over 2. So 3 pi minus 8 over 4 plus pi over 2. Common denominator. Never ends. When's this problem going to end?
You know what I'm going to do when I get home? I'm going to do one of these problems and I'm going to do half of it. And then I'm going to say, okay, that's it.
Etc.
Yeah.
That's a need.
And then I'll wonder, what did I do wrong? I know I did it wrong. And I'll forget that you had to put it all together at the end.
Right.
Yeah.
Exactly.
I usually do that on exams.
Yeah.
Yeah.
That's always the best time to do it, you know?
Why what?
I usually have the problem, and I'm like, what about it?
That should be a 4 on the bottom. Sorry. Thank you. That should be a 4. No, you didn't. No, you're thinking correctly. And it is 5 pi. Yeah, that's right. Okay.
Wait a
Cool.
minute.
Yes?
Why'd you add a pi over 2?
That was the semicircle.
Wouldn't that be pi?
It's a circle of radius 1. So a full area would be pi. The area of a semicircle would be pi over 2.
Isn't a circle 2 pi?
That's the circumference.
Oh, right.
The circumference of the unit circle is 2 pi, but the radius of 1 makes it pi r squared, so pi 1 squared. Cool. Divided by 2. Yeah. Yeah. All right. So we get to do one more problem.
What can we make last for 10 minutes?
I will show you what we can make last for 10 minutes.
The triple integral.
Don't
So,
ask questions you don't want the answer to.
Yes. So we will do one simple question. So here's where we start to get abstractness. We've had very tangible examples up to this point. Very tangible. We can visualize our solid object using the whole upper surface, lower surface model. Now, when we go to a triple integral from a double, notice that with a single integral, the domain is one-dimensional. For a double integral, the domain is two-dimensional. For a triple integral, the domain is three-dimensional. So the domain is a solid. So the domain for a one single integral is an interval. The domain for a double integral is a region, typically in the xy plane. And the domain for a triple is a solid object. So the first thing we want to do is think about a practical example so you just have some sort of concept in your head for a triple integral. So the idea is that we need to come up with a function that is defined at every point of a solid object. So one very common application in physics is to find the mass of a solid object if you know its density at each point of the solid object. So we already did this in the first chapter where we found the mass of a wire by integrating density. You can also find the mass of a two-dimensional region, so two-dimensional density. Integrating that density will give you the mass of that, they call it a lamina, if it's a flat object. Now, if we imagine a solid object, and if the function that we're integrating is the density function, so it's measuring the density at every single point inside that solid object, the triple integral of a function, easy concept, would be to think of it as finding the mass of a solid object if you integrate the density function. So integrating density gives you mass. Another function that is easy to visualize that is a three-dimensional function is the temperature function. So you can imagine the temperature at every point inside of a solid object. Now, integrating that temperature might not make a ton of sense unless you also divide by the volume of that solid object, in which case you would get the average temperature of that solid object. So if you do a triple integral of all the temperatures and then divide by the volume, you'd get the average temperature per point. The simplest example of, I think, is the integration of density gives mass. That's probably the simplest way to think of a practical application for a triple integral. So let's imagine our solid object as being a bunch of tiny parallel pipids. Normally, when we do our subdivisions, normally we think about doing them very evenly. Normally in Calc 1, it makes the most sense to subdivide your interval evenly. You know, you take b minus a and divide it by n. So you have even subintervals. In two-dimensional cases where you have a two-dimensional region that you're integrating over, it makes most sense to make all of them little squares. But you don't have to. They could be weird rectangles of different shapes. It doesn't matter. For our solid object, same thing. We just need these tiny parallel pipids that our solid object is chopped into. Uniform parallel pipids, namely cubes, makes the most sense conceptually if you think about all these tiny little cubes that build up your solid object. And you can imagine the boundary of your solid object. The bigger those cubes are, the more extra space there is, so it's not going to be as accurate. But the smaller those little cubes get, the closer the pile of cubes approximates the volume of your solid object. So same idea with Riemann sums. We take a test point anywhere inside that tiny parallel pipid. That's going to be the ordered triple that we plug into our function that we're going to use as the function value for the whole cube, that whole little cube. So every little cube has a test value. Every little cube is going to have a function value that's determined by whatever that test value is. Then we're going to add them all up. And then we're going to take the limit as the partition goes to 0. So when you're doing a partition of a solid object into these little parallel pipids, the delta there is represented by the longest possible diagonal of all the little rectangular cubes that you have. So if you force all of those cubes or those rectangular parallel pipids, if you force them all to go to 0, then you get the triple integral. So the Riemann sum approximates the integral and then the limit gives you exactly the value of the triple integral. So again, if you think of f as density, that triple integral of density gives mass. And if there is no f there, the triple integral of dv gives you, what would that give you? This
Area? No.
little more. Next step up, volume. Double integral of dA gives area. Single integral of dx gives length. Triple integral of dv gives volume. So the triple integral of a volume differential just gives you the volume of the solid object that you're integrating over. Just like the double integral, if there's no function in there, you're just getting the area of the region you're integrating over. So that's what we're talking about here. Area can be thought of as the double integral of dA, or the single integral of a function gives you area also. So there's these multiple options. Now, when we're dealing with the triple integral, you absolutely have to be able to decide whether you should use lower upper, back front, left right. You need to know which direction has unique surfaces. So if we are trying to find the volume, some weird volume here, we need to know upper and lower. It's the same as what we did with the doubles. If you're doing the double integral of a function, you need to know, if you're trying to find the volume between two functions, you need to know, should I do right, left, front, back, top, bottom? Yeah?
Do you ever need to know past, future?
Great question.
Past, present, and future are all happening simultaneously.
Yeah, but if you want to measure them, then you have to consider them as an axis.
No, it's immeasurable.
That's debatable.
That's debatable.
I don't know. Physics seems to come up with a pretty good way to do it.
Yeah, you can. So what we do with our triples, just like we do with our doubles, the triples, the surfaces that we're using as unique go on the inside. So whether it's top, bottom, left, right, front, back, those go on the inside. And then this part is what we've just been doing. Nothing has changed. That is the same region down in the xy plane, but it could be in the xz plane or the yz plane. But that is going to be the region. That's the two variable thing we've already been doing, where you pick a vertical or a horizontal element depending on what it looks like. The inner one, though, that's where you have to decide which direction do you go. And let's just go to the next slide. So this looks way more complicated than it is, but we've already done all this stuff out here. We've already done that. Right? That's just the double integral over your region, where you have functional boundaries that go on the inner integral. And then this is always the integral of surfaces. So the innermost integral is always surfaces. This, or this. The inner is always surfaces. The outer is always what we just did. Whatever the region R is, pick an element and make it work. Blake?
So this seems like you can just keep taking more and more integrals. So my assumption is you could also do like 4 and 5.
Sure.
So is there some rule that generalizes like multidimensional integrals? Or?
And that's what linear algebra is all about. Linear algebra generalizes all the stuff that we've been doing in calculus in 1, 2, and 3 dimensions. Linear algebra extends that to n dimensions. So it takes all the rules and it just extends it to n dimensions.
Are we just only going to go to 3 though?
We'll only go to 3. Okay. Yeah, we'll go to 3. We'll stick to it. We'll be very practical. All right. Have an awesome Monday. Oh wait, you already did.
It's not over yet.
Core stuff?
Yeah.
If there's no data.